New pictures captured by the James Webb Space Telescope have shocked analysts. Rather than developing our understanding of the universe, these photos revealed an unsettling reality. Our current observations fail to grasp the nature of the universe in its earliest stages. Where our theories about the universe's beginnings reach their limits, we are compelled to contemplate new explanations about its early phases. The question arises: how was the universe formed and why? This new discovery challenges even the most experienced space experts to rethink the Big Bang and the ever-evolving details of the universe's origins. We must reassess the possibility of the Big Bang itself. Contrary to popular belief, the Big Bang was not an explosion in pre-existing space. Instead, it was space itself that began expanding about 13.8 billion years ago, along with matter and time, from a remarkable phenomenon in physics and cosmology. A singularity represents a point where gravity becomes so intense that space-time curvature becomes infinite. Today, after billions of years, we observe that our universe is part of a vast, interconnected cosmic structure. For researchers, this represents a fundamental aspect of the universe. Its very existence and perpetual expansion are critical to understanding that the universe is not moving into pre-existing space. Rather, space itself is continually growing in size. According to conventional theories, the first stars began to shine between 200 and 300 million years after the Big Bang, marking the end of the so-called Dark Age. During this period, the first luminous celestial objects clustered together to form mature galaxies. However, how quickly these galaxies developed remains an ongoing mystery. A significant breakthrough came with the first images captured by the James Webb Space Telescope in July 2022. Researchers announced that the telescope had identified numerous galaxies, some of which existed about 300 million years after the formation of the universe. Compared to the stellar structures formed billions of years later, these early galaxies were significantly smaller and less massive. This observation aligns with a scientific model accepted by experts, which suggests that the density of matter in the early universe was insufficient to form galaxies as large as those seen today. This discovery began with 6 surprising, redshifted luminous spots observed by the telescope. These findings triggered one of the most significant astronomical debates of recent times. Although these newly discovered galaxies are similar in age to previously recorded ones, they are nearly as massive as our own Milky Way galaxy. This has created an intriguing mystery in cosmic cosmology. By examining a series of images captured by the telescope's near-infrared camera, researchers identified the aforementioned light sources using redshift analysis. Experts confirmed that the light from these objects took over 1 billion years to reach Earth, meaning they existed between 570 and 700 million years after the Big Bang. Based on their characteristics, scientists concluded that the telescope had detected 6 massive early galaxies. Surprisingly, these galaxies were so enormous that they defied conventional cosmological assumptions. Instead of finding the expected dwarf galaxies, the telescope revealed structures nearly as large as our Milky Way, despite forming in the universe's infancy. Continued analysis of the data gathered by the telescope shows that these star systems already contained more than 10 billion times the mass of the Sun, with one potentially surpassing the 100 billion solar mass mark. Whether this possibility is confirmed or not, the mystery remains unresolved. If even one of these galaxies is proven real, it would challenge previous assumptions. To account for their existence, the density of matter in the early universe would need to be several times greater than previously accepted. Alternatively, it may suggest that these galaxies formed through an entirely unknown process. These discoveries and the ensuing discussions are prompting further evaluations of the Big Bang theory. Many space experts with alternative perspectives are frustrated, as their views are often sidelined in scientific journals. Even those who continue to support the Big Bang theory face persistent, unanswered questions. These questions include: why and how did something emerge from nothing 13.8 billion years ago? Could something truly originate from nothing, or was there a triggering event? Was it all a coincidence? Stephen Hawking famously pointed out that the concept of time as we know it began with a Big Bang. Thus, this process could not have been caused by an external factor or event. Another unresolved question pertains to the uniformity of radiation and density throughout the universe. Regardless of the direction or distance we observe, we find similar densities and distributions of galaxies, nebulae, and radiation. Current theorists explain this phenomenon through the theory of cosmic inflation. However, others extend this idea further with a hypothesis of turbulent inflation, suggesting that inflation has ceased in certain regions, like bubbles, but continues indefinitely elsewhere. This implies that multiple universes could form within these bubbles, each with its own unique physical laws. Within this model, an intriguing question arises. What if the universe does not represent the totality of existence? More creatively, what if another universe existed before our own? In this case, the Big Bang might be part of a larger cyclical process. Bigger, more perplexing designs inside this model highlight the chance of an everlasting cycle of breakdown and revival of the universe. This has progressed, but it isn't the only perspective introduced in the realm of cosmology. Apart from the theory of how things came to be, in 1955, for example, an article appeared in NASA's Hotshot suggesting that there may have never been a Big Bang, as the universe might have existed for an infinite period. In this view, the expansion of the universe would be non-existent, and the steady improvement of matter could give the impression of consistent advancement. Another fascinating, controversial hypothesis comes from the realm of quantum physics and string theory. Some studies have suggested that our universe and everything in it could be a projection or a higher dimensional simulation. While this may sound like the plot of an intricate sci-fi film, it could relate to the Kardashev scale, which measures the advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully utilizing the power of an entire galaxy, it might have created a perfect simulation. However, determining the reality of such a scenario is a profoundly complex matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of profound mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the very fabric of our universe, challenging established theories and prompting scientists to reconsider fundamental aspects of cosmological understanding. At the heart of this inquiry lies the theory of the universe's origin, a cornerstone of modern cosmology. According to this theory, roughly 13.8 billion years ago, the universe emerged from an extraordinarily dense and hot state, expanding rapidly and resulting in the spacetime and matter we know today. This monumental event was not merely an explosion within pre-existing space but marked the very inception of space itself. The idea of a singularity, where gravitational forces are so intense that spacetime curvature becomes infinite, supports our understanding of this early cosmic epoch. Yet, the discovery of early galaxies by the James Webb Telescope challenges assumptions about how quickly structure formed in the universe's infancy. These galaxies, identified within a few hundred million years of the Big Bang, appear surprisingly developed and massive compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand exponentially. This rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, recent discoveries suggest complexities in the early universe's development that may require adjustments to inflationary models. The formation of galaxies like those observed by the James Webb Telescope forces cosmologists to rethink the conditions and processes that govern the universe's early history. These galaxies, now massive and vast so soon after the Big Bang, suggest a density of matter exceeding previous estimates. The mystery deepens when considering how such large structures could form and evolve in such a short cosmic time frame. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that comprise most of the universe's mass and energy. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical enigmas, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang perspective. Some theories propose that our universe is just one of many in a vast multiverse, each with its unique physical laws and constants. These ideas, emerging from advances in string theory and quantum cosmology, suggest a more intricate and interconnected cosmos than previously imagined. One theory gaining traction is eternal inflation, where universes continuously emerge from a larger inflating space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they push the limits of empirical validation. Another provocative theory posits that our universe exists within a simulated reality, much like a computer-generated simulation. This concept draws parallels to advancements in artificial intelligence and computational science, where simulations can replicate complex systems with remarkable fidelity. If true, our perception of reality as a tangible physical universe could be fundamentally altered, raising profound philosophical and scientific questions about the nature of existence. Moreover, advances in observational astronomy continue to reveal the vastness and complexity of the universe. Telescopes like the James Webb Space Telescope, with its extraordinary sensitivity and resolution, promise to uncover even more secrets of the cosmos. Future observations might shed light on the earliest moments of the universe, offering clues to its ultimate fate and the fundamental principles governing its evolution. Beyond observational astronomy, particle physicists are investigating the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these essential interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the nature of time itself remains a subject of intense debate. Quantum theories suggest that time may be emergent or even elusive at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's origins and evolution. Furthermore, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable environments elsewhere in the universe. Future missions, such as the James Webb Space Telescope's investigation of exoplanet atmospheres, might provide evidence of biosignatures indicative of life beyond Earth. In addition to these scientific pursuits, cultural and philosophical reflections on the universe enrich our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration drive exploration and discussion across disciplines.